order, and the same time first order reactions, second order reactions. Okay, those things were discussed. And as you're all aware that nucleophiles are electron rich, and we can have neutral nucleophiles or ionic nucleophiles, and electrophiles also can be neutral or ionic form. So these topics we were discussing, and the terms like leaving groups and nucleophile entry, and how the geometry is retained or inverted configuration. These all topics we had discussed yesterday. Also, we were looking at conversion of tertiary butyl bromide. When it reacts with any water entities, we get tertiary butanol, or like tertiary butyl alcohol. These topics we were discussing. Now, in today's class, we shall extend our discussion and see what are the other forms of like SN1 we have looked at, SN2 kind of mechanisms, followed by elimination or electrophilic reactions, if depending on the time we can discuss. Okay. So yeah, I still see that there are close to like 17. And
Good morning, sir.
yeah, good morning, good morning. Yes. So these are the main topics where we were discussing about. Okay, so again I insist everyone, you must be aware of why a nucleophile reacts with a carbon center. Okay, and very important point is we should the formation of the carbocation from the substrate is slow step, and the nucleophile, uh, for example, entry and deprotonation are very quick processes. So for SN1 mechanisms, what we have observed is the rate of the reaction or the stability of the carbocation is very good for tertiary butyl groups. Okay, followed by secondary, primary, and CH3 group. Same way, the reactivity wise also, tertiary butyl group has got the highest reactivity, because you see, by inductive effect, all the methyl groups will direct the electron density towards the carbon, and depending on the leaving group, when it leaves, you get a permanent positive charge or partial positive charges, where it creates stability is dominant for tertiary. So reactivity is high, stability of the carbocation also is high. So once it has formed a very stable carbocation, the reactivity also is faster. This part also we were discussing. And we have also, I had asked, I think, I don't know how many of you have looked into this question, like dielectric constant means what you do is, in general, to do a reaction, you take the substrates, like for example, phenol or bromophenol or like that. Take it and put it in a solvent system, and then do the reaction. So if you take the substrates and put them in water or any substance, okay, where the dielectric constant varies from low to high, the rate of the reaction for SN1 mechanism increases enormously. Even this part we had discussed, we have taken for methanol and water example. Okay, for the like bromoethyl benzene, if you have taken this, we want to substitute bromine group with cyano group. So bromine is a good leaving group, cyano is a nucleophile. So Br minus Cn minus will be joined here. So as discussed, the dielectric constant, which has a lot of impact, or for example, the polarity part from the dielectric constant will stabilize the carbocation. Okay, because if you have like non-polar or moderately polar solvents, you cannot have the positive charge very well stabilized. Okay, so that is the reason we should have dielectric constant above uh, like above certain range to make the reactions go very quickly as compared to a moderately polar or a non-polar kind of substances. So this also we had looked at yesterday. So these are the reactants, products, and it goes through an intermediate step where the carbocation formation is the slow step. How carbocation forms. Once carbocation forms, how it reacts with the nucleophile. And once you attack the nucleophile, there is a deprotonation process. Like H plus will go so that the charge will be ROH. Even this part we have looked at, and this is the plot showing reaction coordinate, means how reactants are converted into products with respect to energy profile. This also we had discussed. So you can see that nucleophile, and this is the leaving group, like any bromide, iodide, or like that, nucleophile. And once it needs to pass this activation barrier to form the carbocation. And this is the slow step. Once this activation barrier is passed, you are splitting carbocation and nucleophile, like for example the leaving group, and the nucleophile comes and attacks the electron deficient carbon, and then you make a covalent bond with that along with the um, removal of nucleophile, along with the removal of the leaving group. This topic we were discussing on like yesterday, and I hope by now you must have looked at what is tarslate groups, and it is very important. As I told, we are all the time showing you bromide, okay, iodide, or even for example bromine substituted with cyano group or bromine substituted with OH group. But if you have groups like tarslate or iodide, bromide, these are the good leaving groups. Means if they are attached to carbon atom, they would like to leave away from carbon to make carbocation. Once you make a carbocation, there is an entry of like nucleophile and then making a bond. Okay, so this part uh, also we had discussed. So essentially, in this case, we are looking at, for SN1 reaction, leaving group plays an important role. So the more quicker the leaving group, more stabilized the carbocation, greater is the reactivity with respect to the incoming nucleophile. Okay? These topics we were discussing, and again I'm telling you, you might be aware of the leaving groups and what exactly it does the chemistry. Okay? All the time remember, formation of the carbocation is first important point. Second one is how nucleophile enters and stabilizes the carbon center. Okay, that is a also we have seen. Now, as we have discussed and we just now talked, what are the factors affecting SN1 reaction? We have understood few minutes back that polarity plays an important role because you want to stabilize the carbocation. Polarity plays. So, what are the important factors which affects SN1 reaction is how the leaving groups dissociate from the carbon. Okay, like iodide, bromide, or any such groups which leaves, that is very important factor. The more easier the leaving group leaves, the stable the carbocation forms. Once the carbocation, again when I say the term stable, it is not product stability, it is to look at like the carbocation is very eager to catch up nucleophile. Okay, that I mean by stability. And so that is the reason, the stability of the carbocation. So what it means is, if you have more substituted on the carbocation, like for example, secondary and tertiary, if you compare, you will have tertiary more substitution. And in that also, you can have bromo or different ethyl group, methyl group, propyl group if you have. If you do more substitution to the carbocation, the carbocation will be more stable. We have taken one example yesterday, and also we looked at how the reactivity of nucleophile, it doesn't impact on the rate of the reactions. Even as discussed yesterday, if you take 100 grams of like tertiary butyl bromo compound and 10 ml of water, okay, whatever it's supposed to react with the water or like tertiary butyl bromo compound will only react. Even if you take water 10 ml or 100 liters, it is same, because since it is nucleophilic first order reaction, substrate only plays an important role. Okay, so no impact on the nucleophile. Also, the weaker base, when it is leaving group, and if you have a weaker base, then there is a less tight binding with respect to carbon. Okay, and it is very easier to break. So these are all the factors which affects SN1 reaction mechanism. Now let us carefully look at substitution reaction with halides. We have now, in yesterday's class, we have looked at carbon which substituted with different functional groups, or for example, methyl tertiary butyl group. Now let us take a simple system like methane, which I think many of you are aware of. If you take methane, that to bromomethane, you remove one hydrogen and put bromine and bring hydroxyl group like a base, NaOH, potassium hydroxide or water. If you take, what happens is, we are looking at substitution. So bromine is being substituted with hydroxyl group and bromine leaves. So we get methanol from bromomethane. If you take any base. Here also, if you double the concentration of bromomethane, the rate of the reaction doubles. Okay, means if you take 2 times, then the rate of the reaction increases to 4 times. So, which means there is a dependence of like incoming nucleophile with bromomethane, which means we are looking at dependence of both substrate and nucleophile. And if the concentration of 2, like nucleophile, is doubled, then the rate of the reaction also doubles. Yeah. Now, we looked at no impact of nucleophile to importance of nucleophile, dependence of nucleophile, which brings us to topic what is called as SN2, like substitution nucleophilic bimolecular reaction. The rate of the reaction depends on bromomethane concentration along with hydroxyl concentration. So these are the outcome of, or if you have less substituted groups, for example, only a bromomethane or iodimethane if you have, and here instead of water, you want to keep a base where you get methanol. Okay? So these are the next possibility for substitution nucleophilic like bimolecular reactions. Now, what is the rationale behind this reaction? So we have methane like this. We allow, for example, hydroxide group. We remove bromine leaves. Okay, so you have like this bromomethane, and the one bromine atom leaves, and then you are attaching the hydroxyl group over this. Here also, same part. So same point, like Hughes and Ingold, they have proposed the following mechanism where you see hydroxyl group comes to a place to the carbocation, again partially a transition state like this, where you all know that because of the electron density and halogen will be more directed towards the bromine state. So, and this makes partial positive charges for this carbon, which likes the entry of nucleophile, and then you get a pentavalent carbon, a transition state. You all know that carbon can form only 4 bonds. Once it forms fifth bond, it is very unstable. Once carbon forms fifth bond, it likes to give away one bond so that it can be very stable with respect to 4 bonds. And so you can see that bromine departs and you get methanol. Okay, so you can see how hydroxyl group enters, bromine departs. Now, if you increase the concentration of this, like for example, if you put more methanol, more sodium hydroxide and more bromomethane, there are a lot of collisions. Means, for example, a lot of molecules will come closer and they try to react. This is all about SN2 reactions. So this is what I'm doing. So you can see that this is bromomethane, and whenever that OH comes, how the flipping of the geometry happens, you can see. You can see that earlier how these were positioned, the position of these hydrogens, once the nucleophile enters, it moves away. So this is reaction of methyl chloride. This is chlorine group leaving and entry of hydroxide group. Please observe the geometry. See how earlier it was like more directed towards you. After the hydroxyl ion, it changes its configuration. This is reaction of methyl chloride with hydroxide ion. Let us see what happens if you take ammonia with hydrochloric acid. Can someone tell me what will be the product if you react ammonia with hydrochloric acid?
NH4Cl, sir.
We get ammonium chloride, right? You can see that. Now there is, here we have ammonia and this is hydrogen chloride. Once like nitrogen molecules comes in closer with hydrogen, chlorine departs, or like NH4 plus Cl minus, if you look at it. Here the configuration is retained. Here there is a flipping happening. Okay, so this is the important essence which I would like to highlight to all of you. So you can see here also, like you are allowing the OH minus, like OH minus ion to interact with carbon along with the removal or the transition state of bromine pentavalent carbon, and then the configuration has been inverted. Okay? So many of you know that it forms inverted umbrella kind of configuration. Yeah, you must be already read in your college books also. Let us see what happens, how mechanism of SN2 reaction works. Now, you have, this is the groups, you have three functional groups, and you have a leaving group here, and you have nucleophile. Nucleophile attack from the front side. Okay, now you all know that dashed lines are away from you, and 1, 2, 3 are in one plane. If you look again, R3 is facing towards you. R1, X are in one plane. Okay, more aptly if you look like this, R1, X. So what happens? You already have a nucleophile X here, or sorry, you have a good leaving group here. Once nucleophiles comes and if it want to attack, it cannot happen from the front side. So this is blocked. Whereas nucleophile entry from the rear side. So nucleophile entry and the leaving group departure happens simultaneously. I mean, like it is a transition state. Then once nucleophile sticks, the leaving group departs, which means nucleophile being electron-rich species, it will attack the electrophilic carbon. Electrophilic carbon is here because once the electron density is more directed towards the leaving group, it forms partial positive charge. So this is an electrophilic carbon here, and which makes the entry of rare entry of nucleophile can enter from rare side to form a covalent bond. And front side approach where you have the nucleophile, the same direction you cannot have because uh, you have a blocking. Now leaving group also is electron rich, nucleophile also electron rich, so both doesn't like each other. So only when the leaving group departs, the nucleophile enters. Okay, or that is the reason why they are both in opposite directions. Leaving group and nucleophile both are in opposite directions. You can see here. So nucleophile from the rear side, leaving group front side is the transition state. Okay, so transition state, both nucleophile and leaving group are positioned in one place. This is very, very quick. Once this happens, you get inverted configuration, means electrophilic carbon is inverted. So now you can see that R1, R2, R3. Because it's a rare attack, you can see that this carbon, you might have already seen from the scheme, because it is blocking from the leaving group side, we get electrophilic carbon inverted, because of which we get backside attack. Okay, nucleophile enters from backside, and we get stereochemical, for example, configuration from here to here is inverted. So that's the reason why the molecules has turned inside out. Also, in the transition state, means transition state means both leaving group and nucleophile are in the same situation, but they are not completely gone or they didn't form a bond. All the alkyl groups R, R1, R2, they lie in same plane. Okay, so for example, so you can see like this. One is facing towards you, other one is facing towards me, and other one in the top direction. So this is the same configuration, same plane kind of configuration. Okay. Now, if you look at both the reaction mechanisms, SN1, SN2. In both the cases, we are breaking the CX bond and we are creating carbon nucleophile bond, leaving group and nucleophile. Essentially, very simultaneously. And transition state, where you get the pentavalency of carbon, it is penta coordinated and still it is sp2 hybridized, because you can see we are having this kind of configuration and one nucleophile here, one leaving group here. So it is 5 coordinated, that too it is very short lived. Also, the nucleophile attacks the carbon exactly at 180 degrees to the leaving group, means inversion exactly. For example, if it is coming, nucleophile is leaving group is from here, then the attack of nucleophile is from 180 degrees. If it is from here, leaving group, then the attack from like 180 degrees. So all the time look for it 180, because it is the best overlap where we get the lone pair of nucleophile and we also have a strong leaving group with respect to C leaving group sigma anti-bonding orbital. Let us not so much go into these details, since we do not have molecular orbital theory exclusively, but what you can understand is the leaving group leaves, and to form a best overlap, you should have the attack of the nucleophile at 180 degrees. Then the leaving group, it must be pushed off in opposite side until we get the inversion of tetrahedral geometry. By now, I think you must be aware of how the inversion of the geometry is created, right? Okay, so this is what I was talking about, inversion of configuration, where you have normal umbrella. Once on a heavy windy day, it moves into inverted umbrella. So this is the product what we get from SN2 kind of mechanisms. Again, if you look at the reactants and how we get the products, so you can see that bromomethane, when it reacts with the nucleophile like OH minus, at the transition state, we will be having growth, bromo and hydroxyl group. Both are in inverted, like one is bromine means OH is in 180 degrees. And once how it inversion occurs, you can see here, and then finally at the end of the thing, bromine departs and then we get methanol. So this is how we get the inversion of the configuration, okay, especially with respect to SN2 kind of mechanisms. Now you all know that it is exactly opposite of SN1. So wherever we have seen the highest rates for this, it will be the least or negligible reactions. Where we have seen the lowest rates for SN1, now it is become the highest rates. Now the SN2 reaction rates, it depends on both concentration of nucleophile and the reactants, means substrates. For example, if you replace hydrogens of bromomethane with methyl group, the reaction slows down. Means you start putting more and more, replace hydrogen with methyl, put more methyl, put 3 methyl groups, then the reaction rate drops down. Now, when you have alkyl halide like this, when you are creating, like for example, partial charges, it can lead to only one stereoisomer. I will elaborately discuss. You might have already seen from the inversion of configuration too. What is the table showing is, if you have more substitution in bromo, or like more, if you bring more tertiary butyl group, the reaction won't proceed with respect to SN2. But SN1 very nicely it will go. SN2 doesn't move. And for the mono substituted one, the reaction is very, very quick. For the di substituted, the reaction almost drops. You see that 1200 to 40. And then for the dimethyl substituted bromo compound, the relative rate of the reaction is very less. If you bring three methyl groups, there is no rate of the reaction is negligible. Okay? So this is also the important aspect of SN2 reactions, reactants, and you have products, and you have a intermediate stage where both leaving group and the nucleophile are in, and these are in one plane. So you can see here how with respect to, if you have more bulkier groups, like for example, now we are looking at the mechanism, especially the reaction coordinate graph. If you put more methyl groups, what happens? If you keep more methyl groups, the reaction, you need to really activate it for a larger energy as compared to smaller energy for methyl group, as compared to two methyl groups. Okay, so you want to almost make it like double or three times. Now, we already seen for SN1 effect of leaving group, effect of dielectric constant. Now here, we should look at leaving groups. You all know that fluoro, chloro, bromo, iodine. If you react alkyl halide with a nucleophile like hydroxyl ion, if you have iodine which you want to replace with alcohol, the relative rates of reaction is very high. Then comes the bromine, that is also moderately high. And if you replace chlorine, then it really drops down significantly. When you have fluoro substitution, there is the relative rate of the reaction is almost negligible. So what you understand from this is, the better the leaving group, the rate of the reaction is quicker. So I guess this part many of you are already clear. If you make more very strong leaving group, the rate of the reaction is very much quick. So for example, for the halogen substituted, if you have a very strong base, you will have a better nucleophile. For example, all the time you can take, instead of water, NaOH or KOH or ethoxide kind of species rather than just water. If you put water in this, you always have a competition between SN1 and SN2. But if you have stronger base, these are very better nucleophiles. So again, we also have to take care of the case with respect to protic solvent, like what happens if you have a polar medium as compared to an aprotic solvent. If you have methanol versus acetone, where like you can have like methoxy and like H plus. You can see here how like iodine, because now you can see that electron density moves. Again, do not worry about iodine is a good leaving group than bromine. But if you take potassium iodide and do this reaction, this will form a carbocation, partial carbo. You will have partial charges. So iodine is being replaced, bromine departs. But if you take aprotic solvents, you again remember, if you take aprotic solvents like acetone, the reaction rate is 500 times faster. Why? Because especially if you use protic solvents like methanol, or water, alcohols, where these all have hydrogen bonding ability, which reduces the power of nucleophile. Means this protic solvent, this OH is a very good nucleophile than Ki. Okay, so it reduces the power of nucleophile because you have very strong hydrogen bonding interaction between the solvent protons and the lone pair of nucleophiles. So lone pair of nucleophiles, and then they can form a very strong hydrogen bonding interactions, due to which the protic solvent is not a good system, but aprotic solvent is a very good uh, system where the reaction goes much quicker. Now, these are the different set of reactions with respect to alkyl halides. So, many of you are aware of the first reaction. You have iodide, bring some hydroxyl group, you get alcohol. You may get alcohol, you may get thiol, you may get ether or a thioether, or you can generate amine or an alkyne or a nitrile. Just vary the substitutions. Instead of hydroxyl, take thiol, alkoxide, okay, or any such things. If you take, you get the corresponding functional groups. SN2 is a wonderful mechanism where you can create different functional groups starting from alkyl halides. But only many of you are aware of first one, but you can also generate such kind of molecules. Now, let us end the first half of our class by comparing SN1, SN2. Simple point, SN1, what we have discussed yesterday is, it's a two-step mechanism where you generate a carbocation reacts with a nucleophile. In the case of SN2, it's a one-step mechanism. Transition state, then you get the product. You have rate depending on only the substrate. Here, rate depending on both substrate along nucleophile. Now, you may have the end products or from the reactants products, you get both inverted as well as retained configurations with respect to the reactants. In the case of SN2, we get inverted configuration. And the reactivity wise, tertiary is a very good group for SN1. Methyl is almost no reaction. For SN2, methyl group is having the best, fastest reaction as compared to primary and secondary. So this is what about the comparison between both SN1, SN2. So you have for your syllabus only SN1 mechanism and SN2 only reaction you should be aware of. So what you can expect for a 6-mark or questions or 8-mark question is compare SN1, SN2 mechanisms, where you want to write this along with reaction. Or they will ask you discuss about substitution reactions. So again, you may discuss all these points. Okay. Now, is there any doubt on SN1, SN2 reaction mechanisms and or the effects of solvents and so on? When you're writing the answer also, you need not give so many examples, but you may just write like depending tertiary group will have more reactivity, and aprotic solvents will have good reactivity for SN2 reactions, like that. Just point, no need to show the reactions or something like that. Any clarifications or doubts with respect to nucleophilic substitution reactions? Anyone in the class?
No, sir.
Okay, so let us. Yeah, I hope all of you are around, right? Like there are 25 students now. Let me take the attendance. I think it's all of you are present in here. Now, let us move on to other set of nucleophilic reactions. Like instead of nucleophile, let us take electrophilic substitution reactions. Can someone give me an example of um, like electrophilic substitution reactions? I mean, you may see that, but you can give an example. How many of you already read this Friedel-Crafts reactions in your earlier classes? Did you have this for your college
Yes,
or
sir. Yes, sir.
lab? Yeah, Friedel-Crafts you have must have
Bulk
read.
react. Bulk react.
Yes, sir.
Okay. Now we are looking at the electrophilic substitution reactions where the dominating species is electrophile. Like whatever we have looked at is substitution nucleophilic. Now electrophilic substitution reactions. Especially we are looking at aliphatic compounds in the case of nucleophilic substitution reactions. In the case of electrophilic substitution reactions, let us go to haloarenes. Arenes means like double bonded kind of systems, and halogen which is bonded to them, especially with aromatic ring like benzene. If haloarenes, these are the products. How they are formed is the reaction between benzene and if you halogenate them or like nitrate them or sulfonate, typically Friedel-Crafts reactions or like Friedel-Crafts reactions also other than this. Again, it depends on how the halogen atom is being deactivated by means of ortho para directing. Okay, with respect to the halogen atoms. Now, you may also look at how the halogen atom can be influenced by ortho or para directing groups. This you might get for a short type questions. No need to explain mechanism and so on. You may just write about electrophilic substitution reactions. You can see, I mean, many of you are aware of why we get like ortho directing or para directing from this like different resonating structures of benzene. Benzene with a halogen atom attached. So the first four, we can understand easily how whether it is ortho directing or para directing species. Okay, so this is generally for halobenzenes. Now, what is electrophilic substitution? Simple thing, we want to use an electrophile to substitute this. So you have chlorobenzene, add chlorine in presence of anhydrous ferric chloride. So we get dichlorobenzene, and ortho is very less, minor. Same way, if you want to like a nitrate, you have chlorine, chlorobenzene, you want to nitrate means you get para, high, and sulfonate. Again, why we get para versus ortho? Again, the relative rates, steric conditions, and also which the ring is being directed. For example, with respect to like nitro group, chloro group, all those things will form major and minor product. Same way, if you want to sulfonate, Sulfonate means you want to put SO3H group. Here also we get para as most. For example, if you take this 100 percentage, like like more than like 90 percentage will be getting para, and traces of this will be coming like minor ortho directing products. And in the case of Friedel-Crafts reaction, we can include methyl group, okay, where the para directing is more. Also, we may add uh, chloroacetophenone if you add acetyl chloride, okay, with respect to electrophilic substitution. So essentially, what is important point is we are adding electrophile species into the aromatic substances. Preferably, we are getting halogen arenes. Especially like this essentially part is called as haloarenes. Now the last part in substitution reactions, after the addition reaction, after the electrophilic substitution reaction is also free radical addition reactions. So many of you might have already read the term called free radical. You might be aware of this. Can someone give me one example other than what is there in the slide? Any free radical? Like what is typically you must have heard in your other classes or environmental course. Example of free radical reactions. Anyone? Any example with respect to free radicals? How many of you have heard about refrigerants? Can you think about now? Yeah, what is it? CFC.
Sir,
So
hydrogen peroxide.
fluoro, yeah, hydrogen peroxide also you can consider, because already, as I told, we already have here peroxide, so that is the reason. So we already have this fluoro, uh, halofluorocarbons or like that, where those are very important precursors or molecules, refrigerants, which react with ozone. Okay, so due to which we get the ozone hole has raised or it has increased or like that. Same way, if you take peroxide and you take a double bonded system like alkene and you want to add a hydrogen halide, what you do, you take peroxide species and you shine light, and then you take hydrogen halide along with alkene. Then what happens? Bromine adds to one carbon, hydrogen adds to other carbon. Till now, what we have seen is substitution, replacing hydrogen with bromine, like that. But now what you are saying is literally you are adding one hydrogen here, one bromine here. Now, here this reaction passes through a radical directed way. So we are free radical addition reactions we are looking at. So how we get this radical is, first you take peroxide. So this is a peroxide structure. You cleave them by introducing light. So we are getting alkoxy radical. So literally you're cutting here. This alkoxy radical, if it binds to hydrogen halide, we generate, like you get alcohol and we generate halide radical. This is a very reactive species. You see that electron deficient it is. So it just likes it wants to add to the, it makes an alkyl radical. Okay, so here you form a bond, methyl bromomethyl, and then you form a alkyl radical. This alkyl radical will again react with the hydrogen halide, what you have taken earlier, to complete, to literally add bromo and hydrogen to form an alkyl halide. From an alkene, we can make alkyl halide as the, so this works as free radical addition reaction of haloalkanes from alkenes. Okay, so even this part, I think you must have already read, especially about free radicals. And what we have essentially seen today is we try to substitute nucleophile from methyl groups, okay, where SN1 mechanism, SN2 reaction mechanism holds very good. And we have seen how the solvents play an important role and what happens if you start substituting it with more alkyl groups and so on. We have also looked at electrophilic substitution reactions, where we are looking at electrophilic substitution reactions like electrophile dominating, and there we can also see the substitution reactions like nitro group, chloro group addition, or Friedel-Crafts alkylation. We have now lastly seen on how free radicals, alkoxy radicals, and halide radicals are formed, and they are reacted with alkenes to form alkyl halides. So even this we have seen. Now, if you look at your topics or syllabus, we have substitution reactions, then we follow like free radical addition reactions. Then we are now looking at the nucleophilic addition. Now we have seen free radical addition. Okay. How we can add a nucleophile, literally we can add to the reactions which are also an important class of the reactions, where if you have typically carbonyl groups, so now you want to add carbonyl group is there, you want to add one compound here, one compound here, okay, towards creation of function groups. Now you know that nucleophile is electron rich species which reacts with electron poor species, nucleophile is electron rich species, it reacts with electron deficient compounds. If you want to add, what exactly means is both electron deficient and electron rich should combine to form a single entity. Now, what is nucleophilic addition? If you look at the important points with respect to nucleophilic addition reactions, is you make a new bond between nucleophile and electrophilic carbon of C double bond O, because why we get electrophile is C double bond O, the electron density will be more towards the oxygen side. So carbon gets slight positive, oxygen minus. So this becomes electron deficient. It likes to take a nucleophile. And here it is electron rich, so it likes to take electron deficient. So you are breaking the pi bond, where you are creating an alkoxide group like O minus delta plus. And this, if you protonate alkoxide, you get alcohol. Means you bring some proton somewhere, so you get O minus becomes OH. This is example what I would like to uh, highlight is. So I hope because there are a lot of examples and all, and we are taking a lot of new topics too. So at least you may note down in a piece of paper the reaction or generalized scheme, so that if you again read it, it will be easier from the material. Okay. Or if you want me to uh, go slow or somewhere, you may let me know. But make sure that you at least take down the reaction very, very briefly. If you want me to stop at one place, sir will take down, I'm okay with that. So now you can take down this also, especially nucleophilic addition reactions. How the depending on the reactivity of the nucleophile, there are two cases. For example, when you have a strong nucleophile, like OH minus ions or like that, anionic, it can directly add to carbonyl groups to form an intermediate alkoxides. For example, nucleophile, it is charged, electron deficient, okay, it attacks, you create a bond like this, and you work up, like put some slight acidic conditions like proton conditions, then we get alcohol. And this is the nucleophilic addition under basic conditions with strong nucleophiles. Means basic condition means nucleophile itself is very basic. You can have very nucleophilic cell systems like Grignard reagent, butyl lithium, or a triple bonded carbenes, lithium aluminum hydrate, sodium borohydrate. So you may just take down this part. I know that, or else it will be, when I'm telling, you might feel it is so much topics or like that. But if you write down, it is very easy. Yeah, you can tell me once you have done completing, I will go to the next slide. Especially you can take down the reaction. So can I move to the next one? Can I go to the next slide? How about Yash or Tarun?
Done, sir.
Okay. So
Yes, sir.
we have, yes, yeah. So here, how nucleophilic addition takes place, we have seen, and this happens because of generation of partial charges, and then if you final reacting working up with dilute acid, you create different alcohols. And if you have weaker nucleophiles, again this is more similar to that of SN1, SN2. In the case of SN1, you can have weaker nucleophile. In the case of SN2, you should have a stronger nucleophile. Same way, if you look at weaker nucleophiles, which you want to add to carbonyl groups before being attacked by nucleophile. This you can do By taking these examples, you can see that you take carbonyl groups and you add, for example, you can see how nucleophilic addition under acidic conditions with weaker nucleophiles. So you can see nucleophile is not charged. In the previous example, you have seen nucleophile is charged. Here it is not charged, and when you try to attack the nucleophile, you can see that you are changing the electron density, and then carb cation slightly partial will be formed, and you attack them. Okay, both, and then you add a because you get a proton, so proton would like to take away this base or leaving group to form nucleophiles like alcohols. Of course, whenever you hear the term weaker nucleophiles, you can have water, amine, or alcohols. So these are examples of weak nucleophiles. Only difference is stronger nucleophiles are charged, so they stabilize the carbocation. But here it is more of intermediate state. You may just take down this so that I will move on to the examples now. What I have shown is general reactions. Okay, so can I go to the next slide?
Yes, sir.
Okay. We have taken two cases of adding nucleophiles. One strong nucleophile versus weak nucleophile. Strong means charged, weak means just a bit lone pair of electrons. We are taking the advantage. No. First understand this. Later you may first take down. You may take down once it is understood. How we get cyanohydrates means we are having a ketonic kind of group where cyano means you want to add cyanide group to alcoholic species. How can we get this? You can see here you have two alkyl centers and one carbon with attached to carbonyl group. So you make bring the electron density towards oxygen, so it becomes partially positive. Then you bind this cyano group like potassium cyanide, K plus Cn minus. You may keep here. So it forms an addition like this, but you see you still have O minus because electron density you have moved. This how you can prevent the charges is you work up with acid to form alcohol. So this is nucleophilic addition reaction between hydrocyanic acid, okay, H plus Cn minus. So now we are getting one electron of hydrogen also is more towards the cyano group, and the ketones, because of the polar nature of C double bond O, you make the carbon electrophilic, and then cyano group it makes a nucleophilic attack. Once you get a positive carbon here, electrophilic carbon, it goes and binds here. Okay. So this intermediate, whatever you are getting, you can work up with to form cyanohydride. And we can also have nucleophilic additions with monohydric alcohol. For example, you have aldehyde or ketone, you can add nucleophile addition to get hemiacetols. You can see that COH, no, proton, one hydrogen will take, and one more side you are adding the OH group. Even this you may try to do as an extension or in order to react with aldehydes, which are otherwise very non-reactive. Now, we have now looked at sorry, I didn't give you time enough time for taking down. You may take the first one more. So you may you can also tell your attendance. 01 Rakesh,
Present, sir.
Ilaraj,
Present, sir.
Shashank,
Present, sir.
Arun,
Present, sir.
Harish,
Present, sir.
Srinivasan Reddy.
Present. Present, sir.
Okay, Satvika,
Present, sir.
Amitoj,
Present, sir.
Ayappa Reddy,
The present, sir.
Giridharan,
Present, sir.
Ramchandra Ram,
Present, sir.
Anurag,
Present, sir.
Shubh Verma,
Present, sir.
Karthik.
Present, sir.
Okay.
Present, sir.
Shas. Yeah, fine.
Present, sir.
Okay. Hariharan,
Present, sir.
Surya R,
Present, sir.
Sai Kumar.
Present, sir.
Again, it is the class is not yet over. Okay, do not leave the meeting. Why I am telling is you might take down. That is the reason I had given time, not leave. And Uma Venkat Reddy,
Present, sir.
Rudresh, Rudresh is around. Roll number 20. Okay, fine, Rudresh. Yes. Uday,
Present, sir.
Yash,
Present, sir.
Surya, A.
Present, sir.
Okay. Yeah, we will anyway. Last 5 minutes or 10 minutes, we can discuss again. So yeah, but let us first discuss about the class, and we will finish by like 9:30 today. And any clarifications we can discuss others. Okay, so again I repeat to everyone during the class you may take down, as I told, at least in a piece of paper to remember these structures. If you straight away look at one day before the exam, or if you look at the materials, some parts you will not really understand. So it's always good to at least briefly write down some points. Yeah? Now, let us, in all the cases we have looked at, nucleophilic addition towards creation of cyanohydrins and so on. Okay, where we add the nucleophile to the electrophilic carbon center to form different functional groups. Now, let us look at electrophilic addition. Okay, I don't know how many of you are thinking it is a bit off from the topic, but if you see, it is all in sequence because you first looked at substitution, then you looked at electrophilic substitution, then you looked at free radical addition, nucleophilic addition, electrophilic addition. So we have got all the things as very good sequence. In electrophilic addition reactions, these are, we are creating carbon double bond and carbon triple bond into alkyl halides or alcohol. Simple. You are saturating the carbons. So you know already that addition is opposite of elimination. Elimination means you are removing. You take a saturated carbon and you make into unsaturated, then it is elimination. Here we are looking at addition reaction to prepare different alkyl halides. That too using an electrophile. You already knew that if you have electrophile, which is electron deficient species, which reacts with electron rich species. And whenever you are going to add, you are making a covalent bond between electrophile and nucleophile. So you can see we have a double bonded system, and you add a, see how do you make an electrophile is you have a compound, like take water, H plus OH minus. OH minus is nucleophile, H plus is electrophile. Okay, as simple as that. In electrophilic addition reactions, you take double bond and you mix with a nucleophile which is bonded to electrophile. We get uh, electrophile being added and nucleophile adds to the other side. So it is saturated. Now, depending on how the rate of the reaction, you can have different mechanisms. In this case, in the first case, you can get a carbocation and then it reacts with nucleophile. So you are creating one new sigma bond, CR1 sigma bond, CR1 sigma bond. Now you can see like hydrogen bromide to propene. If you add, we get 2 bromopropane or 1 bromopropane. Can someone tell me what exactly is the difference between one and second product from here and this? Anyone in the class? Can you, or at least you can tell me what is the rule where you add hydrogen halides to a double bonded species or like that? I mean, yeah, I was a bit surprised that is there anyone in the class who can tell me what is the rule where 2 bromopropane is formed over 1 bromopropane? Anyone?
Sir, more stable carbocation.
Carbocation? No, I'm telling which is the rule. What is the rule says the negative part of. Okay, I think I'll give you one more. How do you know that bromine goes to hydrogen? This hydrogen. And this hydrogen comes attacks here. What is the rule called? It is very straightforward. I'm pretty sure you must have read that.
Marconi
Sir, the
coffee.
second,
Yeah, that's all. What is there? Like it is like Markovnikov's rule, right? Yes,
Yes,
that's what
sir.
I think. You what Shivarma you first try to convey is the negative bromine goes to that CHR. I'm asking the rule, so we can straight away go ahead with Markovnikov's rule and anti-Markovnikov's rule, right? So where, oh, sorry, this essentially is referred as like Markovnikov's and anti-Markovnikov's. Again, it depends on several conditions with respect to nature of the leaving group and also, like for example, how it is being added in solvent systems and so on. Okay, in the case of electrophilic addition. Now, is there any doubt till here? So that I will just introduce one small topic today and then we can uh, Any other doubts are there we can clarify?
No, sir.
No. Yeah, I guess it's no for others too. Yeah. Okay. Till now, we have seen substitution with this nucleophile, electrophile, and we have seen free radical addition, nucleophilic addition, electrophilic addition. Simple electrophilic addition means you are saturating the carbons. If it is a triple bonded, you are making it double bond. If it is double bond, you are making it single bond. So that part we are looking at these reactions. Now, let us introduce. I hope you must have already taken this example. Look at. I will not discuss all the things today. This I will just introduce to you. How many of you have already studied elimination reactions in your earlier classes?
Me, sir.
You already studied.
Yes, sir.
Yeah. So I hope you must have studied E1, E2, or did you study all those things? Elimination 1, elimination 2 reactions?
Yeah, sir.
Studied. Okay, good. So what we have now with respect to elimination reactions is a very small topic where we have addition and elimination reactions. Yeah, I think you are muted. Okay. Yeah, I think I muted him. Okay. We are looking at elimination reactions. The name itself says we are removing elements from the starting material. So we have starting material like this, which is saturated. Remove species like both of them. Okay, to make a double bond. What you have seen just in the previous slide is how to saturate. Okay, now we are going from bromopropane to propene by eliminating. So bromine from here, hydrogen from here. Remove it, we get propene, 2-propene. So especially removal of elements to form pi bonds, particularly dehydrohalogenations, means removal of hydrogen, removal of halogen. So you can see hydrogen, halogen are attached to a carbon. And the one carbon which is directly attached to halogen is called alpha carbon. And the one next carbon to it is called beta carbon. This nomenclature, I'm pretty sure you must be aware. Even if you are not aware, remember the halogen will be attached to carbon directly, it is alpha carbon. The next carbon which is attached to after the halogen atom is referred to as beta carbon. Now we should remove hydrogen and halogen. So dehydrohalogenation means hydrogen and halogen removal is termed as beta elimination. Okay, so beta side hydrogen goes and alpha side halogen goes. So this is the mechanism where you remove species like hydrogen, halogen to form a pi bond. So you can see this alpha and this beta now. And you are having a, like for example, H plus it will go and halogen will go as minus. So you should have a nucleophile which can bind to this along with Levy group. So these are about elimination reactions. Okay. Now, what you have for your syllabus is what are the different types of elimination reactions. E1 and E2. I don't know whether you already must have in your earlier classes E1, C2B, all those things. But we had that for our syllabus, even CB and all those things, but we have removed that for convenience and not to have a lot of topics. So even E2, and you should be aware of examples. If they ask you to write a brief note on elimination reactions, you should be able to easily write. Do not explain them, but E2 you have with respect to mechanism. Like how you have SN1, you have here E2 mechanism. Only you should discuss them. Even no need to worry about it. Only if you know the example, it is more than sufficient. Okay. In the case of E2, you should be aware of the mechanism as well. Now, let us complete with this slide, where what are the examples? What you have seen is beta elimination in the previous example, which is a general example. If you look at elimination reactions, how base removes elements like of hydrogen halide from the starting material. So you can see here, you have bromine hydrogen for a 4-membered carbon ring. You take potassium ethoxide, like potassium tertiary beta oxide. If you take this, instead of KOH, H is being replaced by this tertiary butyl group, OH. So this beta oxide group, what happens is it takes away the hydrogen and bromide, eliminates, and then you are forming a double bonded network. So once you get hydrogen will be liking towards to form tertiary butanol, and K plus potassium bromide you get. So we are getting a alkene from a saturated alkane, and we can get cyclohexene. Okay, only one double bonded system. If you take sodium ethoxide, where you can eliminate hydrogen, chlorine. Again, see here also you have hydrogen, here also hydrogen here, but we have shown here exclusively because we are removing hydrogen from here, chlorine from here. You might be wondering why only here, whether it can go from here. Yeah, it can go here. Okay, it can go from here, it can go from here. Wherever you have chlorine, next one you can eliminate. Accordingly, you get ethanol along with sodium chloride. So this we will extend in like tomorrow's class, all about what are the different ways by which the elimination reactions occur, and what is E1 versus E2 mechanisms, how we can compare, and what are the differences, and what are the similarities with respect to SN1, SN2 mechanisms. So this is the general study with respect to elimination, addition, nucleophilic addition, substitution reactions. Okay. Now, is there any doubt on